Round two is here. Welcome to E&M. Guys, don't forget to subscribe and like, but we're going to be looking at E&M. Okay, so seriously, first comment, nice job down there. Thanks for checking in from Camas, Washington, Vancouver, Washington too. Good to see you both. All right, so now let's just start simple and let's build up. So this first one is force due to two charges. So if I have two charges and they have a distance away, that radius is going to be the force of interaction. Okay. The next one is F equals EQ. So this is a more generic one, but this is defining what an electric field is. What an electric field is a force per charge. In other words, if I had a charge, right, let's say I had a charged object, it would be creating this electric field around it, okay? And if I were to put a charge there, it would, let's say it's a positive charge, it would feel a force. If I would put a stronger charge there, it would feel a bigger force. But the electric field defines that force interaction. Units are going to be newtons per coulomb, okay? All right, let's keep going. The next one here is Gauss's law, okay? Believe it or not. Because Gauss's law helps me find electric field strength. So if I have a single little object, what I do is I draw a three-dimensional sphere around it. And so I would say EDA equals Q, this is actually Q enclosed, divided by epsilon naught. So watch this. This thing is going to have these electric field lines coming out. Well, that E field is going to be the same. It's going to hit, it's going to hit this entire surface the same everywhere. Now, all I have to do is add up. What this means is integral of a surface. I have to add up all the little surfaces on this thing. And if I add up all the surfaces of a sphere, it's just the surface area, which is 4 pi r squared. Q enclosed, okay, over epsilon naught. Okay, that's it for a three-dimensional. Now the question is, well, what happens if I have a really long piece of metal that has a line density, which is charge per length? Okay, so it's like a piece of metal that goes like hundreds of feet. The question is, what would the E field look like here? Okay, so what I would do now is I would draw a surface around this. And that surface would be a cylinder. Cylinder with a length L, okay? And so I would say it's the integral of E dA equals Q enclosed. That's going to be a tricky one on this one, okay, over epsilon. So the E field is going to be the same. The area of the cylinder is going to be 2 pi r times length, because it's a cylinder, so you take the circumference times the length. Q enclosed, this is going to get tricky. Q enclosed, if I solve for Q, I get lambda L. So it is density times length is the charge that's in there over epsilon. But if you notice on both sides of your equation, look what happens. The L's cancel. So you have the E field ends up being lambda over 2 pi r epsilon naught. Sorry guys, it's off the screen. There it is. So if you notice, as I get further away, it's not an inverse squared. Okay, like this one. See, that's inverse squared. Instead, this is just an inverse to the power of 1. Okay, so this guy squared, right? So as I go away, it gets weaker and weaker, faster and faster, but this one's going to be a linear decrease. Okay, so next up, plates. Plates. So when I have plates, what I do is I take my Gaussian surface, is I create basically a three-dimensional prism around this thing. And so it'll have an area on top, an area on bottom, and it's going to capture this little bit of charge right here, okay? So I've got the integral of E dA. What this is equal to flux. This is equal to the number of lines, equals Q enclosed over epsilon naught. So that E field is going to be coming straight out. I'm going to give you a visual. The visual is this. Okay, I know we use this for magnetic fields, but the electric fields off of this plate will also be parallel like this. Okay, so if they're parallel like this, that E field is going to be the same. The area, I'm just going to say is area. Well, look at this. If I do this, how many areas do I have? 2 of them. How much charge is enclosed? I don't know. So density is charge per area. So how much charge is enclosed? It's density times area. So now when I solve this, I get E equals density times area over 2 areas times epsilon. A's cancel. So I end up with an E field of density over 2 epsilon. A lot of students every year will be like, I should probably memorize that. And I'm like, that's a good idea. But sometimes, guys, I mean, these are super complex. Watch, sometimes it's as simple as what's the E field away from a positive charge? Well, it's just KQ over R squared. But where did that come from? It came from right here. If I solve for E, I divide by 4 pi R squared. So I have 4 pi R squared. So you see I have the R squared at the bottom. K. Well, what's my K? So I go back to the front page, reminding you where the K is. K is right here. So notice what K is. K is 1 divided by 4 pi epsilon naught. So that's just 9 times 10 to the 9th. Okay. So hopefully, right, you've seen that connection. Hopefully that was cool. All right, so that is electric field strength. Okay, next one is electric field equals negative dV dx. So electric field is negative dV dx. And then one below it is the integral of that is the negative integral of E dr. Okay. Let's talk about what this means. This means that as I have an electric field, my voltages will change as I move through that field. Okay. What this one means is the voltage I have, the potential, I should call it, the potential is I can integrate across that E field through a distance. Okay, so a lot of times how this shows up is when I have plates with a uniform field. Notice when we say uniform field, I can simplify this just to negative ED. And that's usually going to work for when I have just plates. So plates would be like I have a plate and I have a plate, I have a uniform field. Just use V equals ED. That's it. Where it gets tricky is when it's changing, and it's changing its shape, and it's not uniform. Then I have to use my calculus on it. Okay, so that's these guys right there. Now the next one is V equals KQ over R, but notice how it just says summation. What that means is just add them up. Okay, these are just scalars. These are just numbers, so I add them up. So if I'm like, I got this guy, I got this guy, I got this guy, and they're like, what is the potential here? Well, all I do is I find out what are all the V's at that point, and I add them up. That's it. If I have a negative charge, it subtracts. Okay. The next equation on here, they kind of write it, but U equals QV, and a lot of times you'll use it this way. It is delta V. So change in potential is Q times change in potential. So change in potential energy equals change in potential times the charge you move. So as you move a charge through it, that's what you get. So a lot of times that'll be like, I'll like have a positive plate and a negative plate, and then I have a negative charge, and I shoot it out of it. And the question is like, what's my velocity? Well, if they say what's your velocity, I can get the energy from this and set that equal to kinetic energy to find my velocity. Okay, hopefully this is working. All right, it's a lot, I know. Man, we're just now getting to capacitors. Get ready, people. Okay, so this next one, you got voltage is Q over C, or C is Q over V, or a lot of times you'll end up just saying Q equals CV. Okay, because capacitance is just anytime I have pieces of metal or a conductor and I separate them. So what D is how far apart the two pieces of metal are. That's D. A is the area of the plates. A is the area of them, and then K is what we call the dielectric. That's right, dielectric constant. If it's just air or a vacuum, it's just 1. Okay, so anything, if you stick anything in there like a piece of bread or a piece of metal, not a piece of metal, oh, careful, not a piece of metal, a piece of plastic, anything that's an insulator, this K will be here, and it'll change the capacitance. The biggie that happens, I have two situations for capacitors. One is where they're hooked up to batteries, and two is where they're charged and isolated. Okay, these are really my two big cases. So if they're hooked up to a battery, so here's my capacitor, right? It's hooked up to the battery. It has a charge on it, but then let's say I changed my battery. Okay, so notice what I did here. I changed it. Well, what is the thing that's the same in these two cases? Well, if this is an EMF of E, right, that means this potential difference will still be equal to that. So this potential difference will still be equal to that. So the voltages of these capacitors, or the potential differences across them, will be the same. But when I charge my capacitor and then I disconnect, right? So the battery is no longer connected to it. Now when I change it, what stays the same? What stays the same now is the charge. Because if I have a whole bunch of charges on here and so much charges on here, well, that didn't change because it's isolated. So in this case, the Q's are equal, okay? And since Q equals CV, I could say CV equals CV is a way to talk about things. But this one, since the potentials are the same, I can say Q over C equals Q over C. And a lot of times they're going to ask you about energy, which is down here. Okay, and so energy is just 1/2 QV, but a lot of times we're using 1/2 CV squared. Okay, because sometimes you don't know what the charge is and it's an extra step to solve for it. So 1/2 CV squared is going to be the better way to do it. All right, the next ones on capacitance are dealing with what do I do when they're in circuits, right? So if I have a capacitor in parallel, what this means is I just add up the capacitance. Okay, that's what this means. But if I have two capacitors in series like this, I do 1 over C equals 1 over C plus 1 over C. Okay, that's the tricky ones. And the thing that's the same for all of these is whatever charge I have up here, I'll have the same charge here, same charge here, same charge here. So I'll get the exact same charge for all of them. Well, what's going to be the same for the guys in parallel? They're going to have the same potential differences. Next up, when you first connect a capacitor to a circuit, okay? When you first connect it, when I first close switch S, this is going to act like a wire. When it's uncharged, it is going to act like a wire. So just treat it as a wire. Okay, so just treat it as a wire, and then look at your circuit. When it's fully charged, there's no flow. When it's fully charged, nothing flows there. So you look at your circuit this way. Okay. Next up, if you have to do a circuit analysis. So the next equation here is I equals dq over dt. Okay. So if I'm going to look at charging, well, when I charge at the very beginning, so Kirchhoff's loop rule, if I were to go through this guy right here, okay, I would say that the single loop has no potential difference. Okay, that's Kirchhoff's that guy. Okay, and so so I'd say the EMF of the battery minus the potential difference across the capacitor minus the IR. Okay, so I could say 0 equals EMF. Capacitance is going to be, let's see, capacitance will be minus Q over C minus dq dt times R. So when you isolate this, so you want to have your, watch us, move this guy over, so you get Q over C minus epsilon equals negative dq dt times R. So if you see here, see how you have dq? You want to get this back over and the dt over. So watch this. You get dt equals R over Q over C minus epsilon there's negatives still floating around here, times dq. So now you've got something that you can take the integral of and work with. So that was for charging. Discharging is a little bit easier because discharging, I don't have the battery and it's going to be much cleaner. So when I do a discharge, I'm going to get, my loop will be 0. And so I'll have the potential of the capacitor minus IR of my 2 resistors, because this loop now is going to go through here. So now when you do this, you're going to get, right, so you get IR, so you get, what is that? So you get I times R plus R equals the voltage of the capacitor, which is going to be Q over C. So you get dq for dt times, if the r's are the same, I'm just going to say 2r, okay, equals q over c. Get your q's on one side, get your t on the other, and it's going to be a little bit easier to work with. So again, this is a very quick way to do it, but there's the idea. All right, so next one, you've got R is PL over A. Good to see you. All right, next concept here is resistance is PL over A. So what this is this is called resistivity. And so the idea is that a wire with a length to it, this cross-sectional area here will impact it. But remember, cross-sectional areas are all based off of radiuses. So it's pi r squared equals the area. So as you change your radiuses, if I'm like doubling my radiuses, I'm really quadrupling my area. So if here's my first area, if I were to double all the directions, this is my old area, now I have 4 times the area. Okay, so that's the one thing to be watching on those. That's that one. Oh, this is fun. So the next one is the electric field, resistivity. So the electric field is P times J. So let's see what J is. J up here is current density. So J is current per area. Okay. So the electric field in the wire is the resistivity times the current over the area. So the idea being that the electric field is caused by flowing charges in the wire, the area of the wire, and the resistivity. So rarely do I ever see that even tested, but just wanted to talk about it. The next one is I equals NEVDA. Does it say what V is? V stands for velocity. So VD stands for drift velocity. And it's actually how fast the electrons actually move. The electrons don't actually move at the speed of light. They interact at the speed of light. But the drift velocity, that's actually how fast they physically move. So E is the electron charge, V is the velocity, and then A is the area in which it's going through, and N is right here. N stands for number of charge carriers per unit volume. So to kind of see what's going on. So basically the idea is that the current, as the current flows and passes charges, well, the electrons slowly drift. So if we hook up a wire from here to LA, instantaneously they get currents. It's almost instant, right? It's just basically, it just happens at the exact same time. But the electrons slowly drift towards LA. Towards LA or towards Bonneville, I forget. But they drift, okay? That's the idea there. The next one down here is V equals IR. You've seen it. It's your friend. Okay. The next one is resistances in series. I just add up the resistors. The resistances in parallel, I do the 1 over plus 1 over plus 1 over. Okay. The next one, we're looking at power. So remember, power is change in energy over change in time. But we also, in circuits, can say it's equal to IV. Okay. But remember, since V equals IR, I could also substitute in. So they could also be equal to I squared R, right? But then since I equals V over R, I could substitute in and get P equals IV, right? And so I'm going to say P equals V over R times V. So power also equals V squared over R. Okay. Power questions are very common in circuits, but you have to work with them. All right. Now we're getting to magnetic interactions. You're going to notice that all these have little X's on them. So that little X you're going to see multiple times on here means you're doing a right-hand rule. So doing a right-hand rule, so my first is a magnetic force equals QV cross B. So what that means is it's BQV times sine of theta. But normally we just ignore the sine of theta because that interaction is going to be happening at 90 degrees. So we don't need to worry about it. But if you ever need to worry about it, that's where the sine is. So a lot of times people just go, yeah, I'll just use BQV, okay? So that will be either, no, it'll just be this. So I've got a magnetic field, right? And I have a charge enter it. Let's say it's positive charge, let's say it's positive. As that charge enters, it's going to enter this field and it's going to, current is to the right, field is in, thumb is up. It is going to go this way. But notice that that's a circle. So I could say mv squared over r equals bqv. And so I end up with velocity radius equals mv over bq. Say it now. Put it in the comments. Y'all know what you're thinking. It's time for that senior barbecue. All right. So that's usually how we're using that one, okay? The next one is Ampere's law, or as Schmier would say, Ampere's. Ampere's law is where you've got a wire with a current going through it, okay? And what you do is you go, hey, I know what the field looks like around this. It's going to be a circle around this thing, okay? Well, that circle, that magnetic field is going to be exactly the same all around it. Okay, and so here's the idea. This I stands for the current enclosed. So I just stick an I. The B field is going to be the same everywhere. Now all I have to do is add up all the little lengths in this red circle, and all the lengths add up to 2 pi r. So my B field ends up being μ over circumference. This one you need to memorize because that's what it's going to be for every single wire. So you know the problems where it's like I have a wire and I have a wire of 2I. What's the field right here at this distance away? Well, I would find it from each of their wires, and then after I know that, I would add or subtract them depending on which direction it's going. This is going to be using first right-hand rule. I even drew it the right way. Look at that. Good job. Okay. All right. The next equation on here is Biot Savart. Biot Savart law, which is dB equals μ over 4 pi, constant I dl cross r hat all over r squared. It's just here to scare kids. So what this means, this is a unit vector. In other words, it has zero impact at all, okay? And currents are going to be constant usually, so that we can factor that out. So really it's going to be lengths and dealing with r squareds. Okay, so let's just kind of take a look at what that would mean. The most common question you'll see is, what is the field on the inside? Well, this wire, let's say it has a current going through it. That wire creates a magnetic field on the inside. To find out what the strength is, Biot Savart is the only option to get it that I know of. Okay, you cannot use amperes because there's no symmetry. There's no there's no loop you could draw that gives you an easy answer. So what the idea is that you take a little chunk of wire, a little length. Well, that creates a little B field right here, a little baby B field right there, a certain distance away. And what r hat does, this unit vector, what it just tells you is direction. Okay, so these guys are at 90 degrees to each other, so we're all good. So remember that cross product, 90 degrees, so we don't have to worry about it. So if I want to find out what the magnetic field is, you know what I do? I add up all the little magnetic fields. So that's going to be the integral of μ over 4 pi I dl R hat's perpendicular, so that goes away, over R squared. So look at this. B field equals, watch this. I'm going to circle the things that are constants. I is going to be constant. That's constant. That's constant. So watch this. So it's moy I over 4 pi integral of little lengths r squared. Well, these are dealing with lengths here. So ready? So how do I take the integral of that? So that is r to the negative 2. So I add a power. I end up with r to the negative 1. So 1 over r. Okay? Because if I have 1 over r squared, that's the same as r to the negative 2. So I take the integral, I add a power, and divide by a power. So this is going to be negative moy over 4 pi. Oh, Schmear feels broken right now. I got this. I'm going to come back and add an edit to this. I'm making a mistake here. My brain just stopped working. I know I'm going to have to deal with that angle and 2 pi. Why am I not dealing with 2 pi? Oh, Schmear. There's Schmear's mistake. You ready? Ha ha! Watch this. This r doesn't change. Is that cool? So that r squared gets pulled out also. Okay, Schmear's going to redeem himself. So you ready? Here we go. Here we go. And so what is the integral of all the little dl's? Well, they make up a circle. So as you go around that circle, right? Watch this. What is when I add up all those lengths, I get 2 pi r. One of those r's cancels. One of those 2's cancels. Pi's cancel. So you end up with B field is, the quantity is moy I over r. Where'd the 4 go? Oh, that's a 4. Oh. So that's a 2 in the bottom. Dang it. Wish I would have caught that. That's a 4. Hopefully you caught that I screwed that up. There you go. That is Biot Savart law. Watch. So what would the B field be if I only did half the circle? Well, instead of using 2 pi r, I'd use pi r, and so it would be over 4 instead. Okay? So these types of questions, you're going to end up with the same results. I've had students just memorize what the field is inside a circle to save them a little heartache later. But that's up to you. You could do that if you want. Biot Savart. Okay. Next up, we got F Bill. Okay. The force that something feels is just Bill sine theta. And so that's a win for Schmear. And it's on record. Thanks for tubing in, people. And so you've got, have a good one. It's so it's Bill sine theta. And so what the idea here is you can add up all your forces from a wire and see what their contributions are. So that's kind of what this guy's doing here. That's what that one is. Mine is all gobbledygooked here. So let's come back here. Ready? The next one on here is for a coil. Coils will be mu n I. Okay, and the key is the little n is number of loops per length. Okay, so this is, I've got this coil. Good morning. And so I could count my loops, right, along this length, or sometimes they'll give you the density. So this is also, you need to be able to prove this using Ampere's law. So take a look at that. So we did that one in class. All right. This next one is super useful. So this is magnetic flux is the integral of B dA. Well, a lot of times it'll just be B times A, because the B field will be constant. Okay? So where that's going to be useful is our next equation. So we've got EMF equals d flux dt negative. So what this means, a lot of times we'll just rewrite this as negative dBA over dt. Because a lot of times they'll give us the B field and A field. So what this is this is when I have a loop and the field is changing, this can tell me how much voltage I'll get, how much potential difference I'll get. So this stands for EMF, okay? That's what this setup is here. All right, the other one that is not on here that comes out of this is BA over time can turn into BLV. And this is if I have a wire moving at a velocity through a field. A lot of times this is the easiest way to do it. Okay, just do BLV. You also know there's a sign involved in there. Okay. Last ones down here are dealing with inductors. So what an inductor is if I have a circuit and a coil and a resistor, okay, an inductor L and a resistor R, at the very beginning it will resist a lot. So it'll have an EMF of negative L over di dt. What this means is as the current changes, it has an EMF. Because remember, I have to have changing, when I have a changing field, I get an EMF. And so if I have a changing field, I have an EMF. So when do I get an EMF? When I have a changing current, because the current's going to give this coil its field. Okay? You're never going to have to solve for what L's are. They're going to give you L. Maybe a lab question where you have to solve for it. And so a couple different ways you could do this. So the other one is to do 1/2 Li squared. And so you could look at the energy that's stored. So one is to measure the EMF, but the other is to measure the energy. Because I could look at when this thing fully charges, I could then disconnect it and make a loop, and I can look at the energy involved. Okay, so just like Kirchhoff's loop rule, for a loop, I should get rid of this because the kids looking at the paper later are going to freak out, is going to be 0. So I could say the battery minus the EMF of the inductor minus the IR. Okay, so the current is going to be changing, but watch this. 0 equals EMF minus L di dt minus, good morning, minus IR, but that's a negative and a negative, so we get this. So look what you get. So you see how you have di dt and you have I? You can now isolate them and you can do some calculus with those. Again, this is going to be minimal on the test, but now if I get this on one side and these on the other, I can now isolate di's and i's and solve it. Great resource for this is Hyperphysics, to do a walkthrough and just look up inductors. Okay. All right. That is the biggies. I'm trying to think what else is there. That's the biggies. Guys, right-hand rules. Let's do this. First right-hand rule is I have a wire with a current in it, and it produces, take your right hand, your thumb goes here, and it produces a field, a magnetic field. And the magnetic field is going to be μ over 2 pi r. Okay, that's my first right-hand rule. My second right-hand rule is I have a coil. Okay, and let's say the current's going to the right. What I do is I grab the coil in the direction of the current, so it's going up the front, down the back, and the thumb ends up being the magnetic field. Okay, so the field ends up going in this way, into the right. Okay. Third right-hand rule, okay, ready, is you've got, let's just draw it. Let's say this is a B field, and this is a wire with current I. Okay, current is up, but which way is the field? In. So my 3 fingers are the field, it's in. My thumb is the force. So again, pointer finger is the current, 3 fingers are the field, thumb is the force. Okay, what are the equations? F equals Bill, and F equals BQV. Okay. Fourth right-hand rule is and so if I were to move a wire through this field, so ready? So here's your last right-hand rule. My movement is my thumb, so it's moving this way. Pointer finger is the field, you point with the field. And then your eye ends up being this way. So you end up with a current up the wire. And if the current goes up the wire, then this would be positive over here, this would be negative. But if you connected it to something, then it would have a current flow that would happen. So the equation for this one is Journey Song. Nailed it. Don't Stop Believing by Journey is how you remember this one. Good job. So you got BLV. Journey, you like Journey? Patrick is mildly ambivalent about Journey. Okay, so we've got ourselves EMF equals BLV. So knowing the B field, knowing the length, and knowing the velocity, you could find out what the voltage. Well, voltage equals IR. They could also ask you questions about power. So there we go. I think we hit everything, even with a screwed up Biot Savart in the middle. Ampere's law. Don't forget to subscribe and like. Guys, keep those comments clean. Thanks for tuning in. Go Union. Hey, game day. Here we go. This video is actually endorsed by Chris Pratt. Just want that out in the open. Have a good one.